So, third speaker this afternoon is Victor Alves, who's going to talk about the Polya-Tchebotarev problem with semiclassical external fields.
Thanks, Antonio. So, I would like to thank for the opportunity to talk. So this is based on one of the works that I did, that I finished on my PhD. It was done with Guilherme Silva. It's about this Polya-Tchebotarev problem with semiclassical external fields. So let's start with some background and motivation. I just need you guys to understand one definition to really understand the problem. It's very easy to enunciate. So given a compact set K in the complex plane, let's denote by M of K this set of Borel probability measures supported on K. We define the logarithmic energy of the set K as the minimum of these logarithmic energies over all this family of measures. This was already presented in the previous days when this is like the Riesz measure when S is equal to 1 or something like that. And this minimum above is attained at a unique measure mu K that we call the equilibrium measure of K. So for every compact set, you have this equilibrium measure. So just with this definition, we can enunciate the Polya-Tchebotarev problem. So fix your favorite collection of endpoints, call it C, and let K of C be this family of all the connected compact sets that contains your fixed family of points. You need to find a K0 in this family of sets that has the maximum logarithmic energy over all possible K. So this is a maximum problem, right? You are maximizing this minimization energy. Okay, but some interesting applications just to continue. So there is like some connections with approximation theory. For example, imagine you fix a function that is an analytic germ of a function at infinity. Let's say, for example, f of z is given by this form. So it's like this m square of a product of these rational functions. And seek polynomials Pn and Qn minus 1, where these indexes are the respective degrees, such that when you multiply your function f by Pn and subtract Qn minus 1, you find a 0 of order n at infinity. So basically, you're just plugging the series, the Laurent series of f at infinity and seeking conditions on the coefficients of Pn and Qn minus 1. Our result of Stahl says, well, it's actually many more things. He was studying by the approximations, that the zeros of Pn accumulate to the Polya-Tchebotarev continuum associated to C, where C is exactly the branch points of the roots that you are defining in F here. So let's see an example. So here I took a fourth root with points Z1, Z2, Z3, and Z4 as in the slides, and I calculated the zero of the P80, the eighth denominator of the Padé approximant. And as you can see, the zeros are trying to draw a specific curve on the complex plane. This is actually a branch for that fourth root of the previous slide, and it is the branch with the maximum logarithmic energy. So this is a very interesting thing that is happening at the zeros of these Padé approximations. Okay, another interesting connection comes by orthogonal polynomials. So imagine you have a set F, and you let Pn be a polynomial of degree n that is orthogonal to every monomial of lower degree. Of course, this means that it's orthogonal with lower degrees polynomials. But for every n, you're looking at a different measure that I'm calling Wn of z dz, given specifically by that formula for some analytic function phi. So n is growing, you're changing the weight and picking the nth orthogonal polynomial. So the description of zeros of Pn will also be given by a Polya-Tchebotarev problem, but this function phi that is, the variance in n will create a deformation at the level of the logarithmic energy. And this asymptotic description will be given in terms of the weighted logarithmic energy. It's a similar definition. So you look at the probability measure supported on the set, but now there is like an external field component. So it's the logarithmic energy plus 2 times the integral of psi of x, where this psi is going to be the real part of the phi function that appeared in the previous slide. This is an extremely general formulation. You need some assumptions on your set and on psi, such that this infimum is attained. And whenever it's uniquely attained, we are going to be called the equilibrium measure in the external field. And this motivates us to consider these weighted Polya-Tchebotarev problems, which is pretty much the same thing, but now instead of maximizing just the logarithmic energy, we are maximizing the weighted logarithmic energy with the presence of the external field. But now, since we are introducing external field, we can actually just consider more general sets. You don't need it to be a compact, because in the presence of an external field, you may have finite energy even for unbounded sets. So now we have a class of closed sets and an external field, and our task is to find a maximization on this class. Well, going back to the orthogonal polynomials motivation, there is this theorem by Gonchar-Rachmanov in '87 that, well, sorry, the first line is not supposed that. So if you assume that there is a solution for the weighted Polya-Tchebotarev problem, and the complement of the support of the equilibrium measure is connected, in that condition, the zeros of Pn, the orthogonal polynomials, will equally converge to the equilibrium measure of the set. By that I mean that if you take any bounded continuous function f, and you do the integral of f with respect to the zero counting measures associated to the polynomial, it's going to converge to the corresponding integral with respect to the equilibrium measure. So this creates an interesting question. How can we find solutions for these weighted Polya-Tchebotarev problems? Without the weight, there is if K is compact, well, for the Polya-Tchebotarev problem, the solution always exists. Here you need to be more careful about the family of sets and the external field that you're considering. Okay. Now I'm going to be talking about admissible problems. By that I mean, which kind of problems did we tackle? So let's start with the external fields of interest. It's going to be some semi-classical external fields. They are going to be given by the real part of phi, where phi has a rational part given by P over Q, and this logarithmic part, a logarithmic sum. Here we assume that P and Q are polynomials where the numerator has at least 1 degree more than the denominator, and that these coefficients of the logarithmic part are all real and non-zero. In this setup, there are going to be n sectors in which your external field psi goes to plus infinite, Iz goes to infinite, which are given by these sets where these theta j's are these sectors, Sj's, where theta j is the center angle of the sector Sj. All right, so what are the curves that we want to maximize this this functional? We are motivated by families coming from classical orthogonal polynomials. So our sets of interest should be a finite union of 3 types of curves. Jacobi type curves, so you take 2 fixed points and you connect them by a curve. Laguerre type curves, you take 1 fixed point and you go to infinity with a curve in satisfying this condition that the external field will blow up. Or Hermite type curves, which are just unbounded curves that goes to infinity only in sectors in which the external field also explodes. Well, it's better to watch an example, right, to have in mind, have a good idea of what kind of sets are we looking for. So imagine I fix 3 fixed points, C1, C2, and C3, and I say, okay, I want a curve that connects C1 to C2. This is going to give this gamma 1. I want a curve that connects C3 to infinity through sector, let's say S1. So I'll have this curve gamma 2. And maybe I want to connect infinity to infinity through sectors S2 and S3. This gives you a curve of type gamma 3. How do we codify this family of curves? Well, there's actually 3 objects. You need a partition of the set of fixed points. This tells you which fixed points are connected to each other. So in this example, my partition of fixed points is the set C1, C2, and the set C3. I need a function that takes the class of the partition of fixed points and gave me angles in which I'm going to infinity. So for example, since C1 and C2 is not connected to infinity, I put these functions as the empty set. And since C3 is going to infinity through S1, I put the function at C3 to be the angle theta 1. And finally, over the set of all possible angles, I define these connections that are not related to fixed points. So on the set of the angles, I also put a partition that tells me which sectors around infinity are being connected without touching any fixed point. So this is just a codification for this type of problem that we want to tackle. And the main result is that for every choice that you made for this codification, there is an element on the class that maximizes the energy functional, which means that this F0 is a solution to the weighted Polya-Tchebotarev problem. Okay? And well, we put this paper in archive a while back, and a couple of months later, Marco Bertola made a numerical program that can calculate some Polya-Tchebotarev continuums. It's pretty cool. You should check it out if you have some interest. For example, here there is like 3 fixed points, and it's going to infinite through these 2 different sectors with like a polynomial external field. It's like there's some cool images that to be done with this. All right. So what is the proof? So what is the proof strategy? So I'm going to talk about a little bit of how we tackle this problem and ideas on how to solve it. So actually, like a way to deal with these Polya-Tchebotarev problems and max-min problems in family of sets was already presented by Rachmaninoff 25 years after his work about these orthogonal polynomials. He basically presents an ideal scenario in which you can find a solution. So let's take a look at the hypothesis. So we assume that psi is an external field. This F hat will be a family of closed sets. And psi is harmonic outside of a finite set, or psi satisfies that condition. The class of sets in which you're looking at the max-min problem needs to be closed in the Hausdorff metric. The Hausdorff metric is the metric of the drawings, right? Convergence means that the drawings are converging. And every element has a upper bound in the amount of connected components, a uniform open bound. So all family does not satisfy this condition, and I'll come back to it in a second. Well, the third condition is just to make the problem well posed. The supremum of energies must be real. There is a technical condition. Over these 4, you can find an element in the class that maximizes the energy functional. So the problem is that we are looking at curves, and curves are not closed in the set of the Hausdorff metric, right? You can make some piano curves that are like the sequences of curves that are filling out a whole 2D space, and then in the limit, you're not going to be finding a finite union of curves. You're going to be finding 2-dimensional objects. So for that class of sets in which we consider the max-min problem, you need to be very careful about taking the closure of the family and applying Rachmaninoff's theorem. So what is this strategy? Inspired by the work of Arno and my advisor for polynomial external fields, we are going to do the following. So first of all, we need to check that the problem is well posed. This comes from the geometry of the class that we consider and the fact that psi is semiclassical. Then we go to a subclass of our family, which better geometry, where the max-min problem is equivalent. So basically, we throw out sets that intersect regions where the external field is super negative. If a set intersects this region, basically it's going to be far away from the max of the max-min formulation. Then, on this refinement, we use Rachmaninoff's theorem for the Hausdorff closure. We need to study the geometric properties of the support of the equilibrium measure of this solution candidate that we found. And finally, we need to construct a set on the family that we are considering that has the same equilibrium measure. Since the energy is defined as the energy of the equilibrium measure, this is going to show that F0, the set that we constructed, this is a solution to the max-min problem. What is the problem with this strategy? The moment we use Rachmaninoff's theorem on the closure, we are not looking at curves anymore. So there is a chance that the support of our equilibrium measure could have a 2-dimensional part, and therefore there is no way to really construct this F0. Okay. So let's go on to the proof, and I'll explain how we deal with that. So the conditions imposed on psi and f imply that this energy functional is upper semi-continuous with respect to the Hausdorff metric. And now, since our class is closed, there's going to be an element that maximizes. That's pretty much the idea to get an element. This is analysis 1. Upper semi-continuous function in a compact interval has a maximum. Then we fix that maximum and start to doing some small deformations of it as a set. So we look at these functions. You fix a function h that is good enough, and you do very small deformations, this big h of t, such that for very small t, f of t, just the image, is still an element of your class. For every direction h, we can define a derivative which is just the derivative of the energy functional. And since F0 maximizes the energy functional, its derivative must be equal to 0. This creates the notion of a critical set, a set that is critical in the sense of this definition for derivative interactions, right? But this family of deformations also induces deformations on the measure level by push forwarding. And you can prove that when the energy is finite of your set, let's denote just on this slide this nu as the equilibrium measure, the derivative of the energy of the set is actually the same as the derivative of the energy of the measure, which is quite surprising in my opinion. In particular, the equilibrium measure of a critical set is a critical measure. Roughly, it's a saddle point of the energy functional, but not necessarily minimal. And this is pretty surprising because when you do these deformations nu t, well, okay, the equilibrium measure is the minimizer of all the measures in the set. But when you're looking at nu t, you're leaving the set, and still this derivative is equal to 0. So it's a little bit more general than just the minimality of the equilibrium measure by itself. Okay. So what is the cool thing about critical measures? Well, after some work, you can show that the Cauchy transform of a critical measure will satisfy a quadratic equation of this form. So this is the Cauchy transform. Then plus the derivative of the complexification of the external field, this big phi, squared will be equal to a rational function. And this rational function is implicit, but there's many useful properties that you can describe, given in terms of the external field. You can prove a result that is very similar to a Studi inversion formula. Normally, Studi inversion in real line allows you to get the measure from the Cauchy transform. Here you cannot get the whole information of the measure, but at least you will know that the support of the measure, the critical measure, is contained in smooth curves that are trajectories of this quadratic differential. I'm not going to go into the details about this, but this is pretty nice because now this support may be, the support may be just a finite amount of curves, which gives us hope in creating a contour that has the same equilibrium measure. And finally, we can prove that if mu is a critical equilibrium measure, which is the case when you take a maximizer set, the support of mu is a compact set made of finite union of analytic arcs. So at this point, you have hope on finding a set that has the same equilibrium measure, and this guy can be a finite union of curves since now the measure is also a finite union of curves. After this, you need to, you already have all the information you need about the geometric properties of mu. You basically need to use some potential theoretical tools to construct the set F0 that is still in the same class and has the same equilibrium measure. This part is more technical. I didn't put in the presentation. So thank you all. And that's pretty much it.